All right, in this topic, I'm going to be talking about discrete probability distributions. Now, this is a very easy transition from the last topic, probability. The basics of probability or the foundations of probability, to this particular topic. So, in discrete probability distributions, two things I want to emphasize first before we get into the actual probability distributions. So the first one is the concept of a random variable. So we're going to be talking about, in general, two different types of probability distributions, the discrete and the continuous. So discrete and continuous probability distributions we deal with in very different ways. So that distinction between discrete and continuous data is very important here. If our experiment is dealing with discrete data, we calculate probabilities one way, and with continuous data, we look at that a completely different way. So in this particular set of notes, I'm going to be focused specifically on the discrete case, discrete probability distributions. So a random variable is very similar to, a random variable is very similar to the concept of a variable in algebra. A variable is a placeholder or a symbol that represents an unknown number. In the case of random variables, a random variable is a variable that represents any possible outcome of an experiment. So, for example, if you are rolling a single die, there are 6 possible outcomes. So the die could land on 1, 2, 3, 4, 5, or 6. In that case, the random variable has a domain of those 6 numbers, 1, 2, 3, 4, 5, and 6. So the random variable could take on, normally we use the letter x, could take on any value that corresponds to the outcome of an experiment. So like I said, we'll talk about two different types of random variables. In this set of notes, we'll focus specifically on the discrete case. So let me switch here. So we'll focus specifically on the discrete case. Ignore this. Ignore the chapter 5, chapter 6. That's left over from a previous class. Okay, so a discrete random variable could be infinite, has either a finite number of values or a countably infinite number of values. What that means, like this idea of countable, this means if you choose any particular data value or any particular outcome, there's always a well-defined next value. Continuous, for continuous, that's not the case. Continuous random variables deal with continuous data, which is measurable, not countable. So here's a few examples. Determine which of these are discrete random variables, which are continuous random variables. So the first one is the cost of a randomly selected orange. So our variable here is cost. So if I choose a random cost, it could be anything. So let's say the cost is $2.37. It makes sense to ask the question, what is the next possible cost after $2.37? So we're working in increments of 1 penny. So the next possible cost after $2.37 would be $2.38. So this is a discrete random variable because given any one value or one outcome, there's a well-defined next possible value. Next one, number of phone calls between Boston and Philadelphia on Christmas Day. Again, number of phone calls. If you pick one value at random, let's say 37 calls, and you ask the question, what is the next possible value after 37? Well, that's well defined. It has to be 38. You can't have 37.2 phone calls. So again, that is a discrete random variable. The next one, the height of a randomly selected student? Well, for height, it doesn't really make sense to talk about what is the next value. So let's say 68 inches. So one student is 68 inches tall. What is the next possible value after 68? Well, it's not 69, because you could be 68 and a half inches. It's not 68 and a half, because you could be 68.1, or 68.01, or 68.00001. So there is no next value after 68. So this height is measurable. This would be height is a continuous random variable. And the last one, breaking time. So again, time. Let me pick a random time. Let's say 7 seconds. What is the next possible time after 7 seconds? Well, again, you can't say 8 seconds. Because what about 7.5, or 7.1, or 7.001, or 7.00001? So height and time, these are measurable quantities. So it doesn't make sense to talk about the next possible number. So for cost, for number of phone calls, these are discrete. For height or time, these are continuous. Okay, so now a discrete probability distribution, or a probability distribution for a discrete random variable, is a list. It's usually given in a 2-column chart. It's a list of every possible outcome. So that's over here, every possible outcome and the corresponding probability. So the value of x, or sorry, the x value of 0, for example, has a probability of 35%, and so on as you go down the table of values. So basically, in the last topic, probability, we answer the question, okay, here's one outcome. What is the probability of that one outcome? Now, in the context of probability distributions, we basically list all possible outcomes and give the probability of each of those possible outcomes. Okay, and so again, here we're focusing specifically on discrete random variables, but this topic of probability distributions is a very broad topic, and probability distributions are classified in 2 ways, on this classification of discrete versus continuous data. So again, ignore the chapter 5, chapter 6 part. So discrete probability distributions, this is a somewhat broad topic. There are specific types of discrete distributions. So for example, binomial is one, Poisson is one, hypergeometric, and others. There's more than just these. We'll talk about a few of these, but there are many types of discrete distributions. And in the context of continuous distributions, we'll talk about these later: normal, uniform, exponential, so on and so on. Here, the normal distribution will be the most important, but again, our focus here is on discrete. But the emphasis here is that there's the label discrete and continuous. These are sort of general labels, and under each label, there are many specific types of each distribution. Okay, so here's an example. In the last topic, when we were talking about specifically just probability, or the basics of probability, I could have asked the question, if you roll 2 dice, what's the probability of rolling a 6? Okay, so down here, what's the probability of rolling a 6? What's the probability of 6? Well, the definition of probability, so the probability of rolling a 6 is the number of number of ways you could roll a 6 and the number of simple ways you could roll a 6 divided by the total number of possible outcomes of the experiment. So when you're rolling 2 dice, you have 6 possibilities for the first die, 6 possibilities for the second. 6 times 6 is 36. So the total number of outcomes is 36. If you're rolling a 6, well, that could happen a number of different ways, a number of simple ways. You could roll a 1 and a 5. You could roll a 5 and a 1. You could roll a 2 and a 4 and a 2, or you could roll a 3 and a 3. So there are 5 ways of rolling a 6. So the probability of rolling a 6 would be 5 over 36. So this would be a problem in the last topics, the probability of an event. Now, in the context of probability distributions, instead of looking at this, instead of looking at the probability of one specific event, we look at the probability of all possible outcomes. So over here, 6 is one of those outcomes. But this is the probability distribution, this table of values. So a probability distribution lists all possible outcomes of your experiment and the corresponding probabilities of each outcome. So if you're rolling 2 dice, you could roll anything between 2 and 12. So the probability distribution lists all possible outcomes, 2 through 12, and the corresponding probabilities. Okay, another problem we looked at earlier was I think what we did was the probability of if you have 3 children, what's the probability of having 2 boys? Something like this. So in descriptive statistics, so here, this is descriptive statistics. We covered the topic of a frequency distribution. And we talked about the mean and the standard deviation of a frequency distribution. In probability, we looked at the individual probabilities for specific events. And now, currently, we're sort of merging those two ideas, the idea of a distribution or a table of values, and specifically the probability of each outcome of the experiment. So currently, this is what we're looking at, the probability distribution of an experiment. And just like before with the frequency distribution, we talked about the mean and the standard deviation of a frequency distribution. We talked about the same thing with the probability distribution. So what's called the expected value of a discrete random variable is the mean of the probability distribution. And formula for this is the summation of x times p of x, or take each x value times the corresponding probability and add them up. So I'll use this example, roulette, to explore the idea of the expected value of a probability distribution. So in roulette, you have 38 possible choices. So you pick one of 38 numbers. If your number comes up, you win. If your number doesn't come up, you lose. And if you win, you're paid $35 for every $1 you bet. So what I want to do is first create a probability distribution for the random variable, and then determine the expected value of a $5 bet. Okay, so with the probability distribution, there's only 2 possible outcomes. You either win or you lose. So we're thinking, in this case, about a $5 bet. So if you bet $5, one of 2 things is going to happen. You're either going to win or you lose. So if you win, you're paid 35 to 1, or $35 for every $1 you bet. If you lose $5. So there's 38 possible outcomes. One of those outcomes is a win. The rest are a loss. So in our probability distribution, the probability of winning 1 out of 38, and the probability of losing is 37 out of 38. And the outcome, if you lose, you lose your $5. If you win 35 times your original bet, or 35 to 1. So 35 times 5 is 175. So here's the probability distribution. We have our outcome, and we have the probability of that outcome. Now, when we're talking about the expected value, we take, and down here I have the formula, the summation of x times p of x. So if we take x, which is, in the first case 175 times p of x, we get 175 over 38. And if we take, in the loss case, x times p of x, we get 185 over 38. So this formula down here says to calculate each individual value and then add them up. So the expected value for this particular experiment is negative 26 cents. So what does that mean? That means, on average, every $5 bet has an outcome of negative 26 cents. Or the casino is expecting, on average, to make 26 cents for every $5 that is bet. So, not looking at any one particular day or one particular bet, but over the course of a year or over the course of many months, this is what the casino is looking for. This average expected value. So over time, the bets are going to sort of average out to this value. Every $5 bet, the casino is expecting to make about 26 cents. Okay, so that about does it for the general topic of discrete probability distributions. I'll get into more specific cases in the next set of notes.